So as we learned last time, carbohydrates are cyclic hemiacetals. Most of the sugars we'll deal with come from aldehydes, where the carbonyl carbon is on C1, or the hemiacetal or anomeric carbon is on C1. We'll see a carbohydrate maybe a little bit later today called fructose, where the hemiacetal carbon is actually C2. In its open chain form, fructose is a ketone. But for this glucose, and recall last time I told you this is how we draw glucose when we mean a mixture of alpha and beta anomers with the little squiggly line. You can do reactions with this C1 hydroxyl group that you can't do with the other hydroxyl groups because of its hemiacetal nature. So imagine in the presence of an alcohol, an excess of alcohol with a catalytic acid, and imagine you're removing water. What we're going to do is basically the same thing we did in chapter 14 with acetal formation, only in this case we're starting with the hemiacetal. So what happens is you protonate the OH on C1 with your acid, generating this oxonium ion where you've turned the OH into a good leaving group. Then electrons kick down and the leaving group leaves. And recall, you've seen this before. We did something like this in the first step of mutarotation. But recall that your text will sometimes show this same exact step as occurring via the leaving group at C1 just leaving on its own. In the mechanism drawn above, it looks a lot like carbonyl chemistry. In the mechanism shown below, it looks a lot like SN1 type chemistry, where the leaving group just leaves on its own. But as I argued last time, these are two equivalent representations of the same step because they lead to resonance structures of each other. Do you see how the molecule that I'm drawing right now with a positive charge on the carbon is a resonance structure of the molecule above that has this carbon-oxygen pi bond. We called this intermediate an oxocarbenium ion. We've also called it an oxonium ion. Either of those terms are okay. But I want you to have the idea that both... What is that about? Students, faculty, and staff. Whatever. Sorry. Better? Okay. That both of these are okay. So you'll see a mechanism like this in your text. That's fine. You can also draw it like this. That's fine too. Don't be confused. They're both identical. All right. Once you get to that oxonium ion, forming the acetal involves attack at the positively charged carbon. Now understand that this attack may occur from either above or below. And because the carbon, C1, is sp2 hybridized and planar, attacking from above or below should happen with similar frequency. Now, the top face of this cation is different from the bottom face of this cation because of the stereocenters at C2, 3, 4, and 5. In other words, a nucleophile approaching from the bottom doesn't see exactly the same things as it does when it's approaching for the top, so there can be a preference for attack from the top versus the bottom. Nevertheless, you would expect that preference to be small, and therefore you would expect to get both alpha and beta anomers. And the way you would draw that is just, again, the little squiggly line to the methanol with a positive formal charge on the oxygen. And then to get to our final product, our acetal product, we would use the conjugate base of our acid to regenerate the acid catalyst, to deprotonate the oxygen from methanol, and get us to the final product, which is the methyl, what we will call the methyl glycoside of glucose. Glycoside is a word for carbohydrate acetals. Okay? So there's nothing new in terms of mechanism there. It's all stuff that you've seen before in chapter 14. It just so happens that this is occurring in the context of a carbohydrate. All right, questions about that? All right. So let's talk about making glycosides where the alcohol is not just a small molecular weight alcohol, but where the OH group of the alcohol is actually another carbohydrate. Okay? So imagine, let's see. Imagine combining two glucose molecules together. So here is the first. And then here is the second. We'll just go ahead and make this the beta anomer just for fun. Okay, so focusing in on, well, actually take a look at that carbohydrate. We'll call this end A and we'll call this end B. Which one of those two, A or B, is an acetal? A. C1 in A is the acetal, right? You can tell that's an acetal because the two oxygens attached to the anomeric carbon, carbon 1, are both OR groups, okay? So that's A has the acetal. How about B? What is carbon 1 in B? Hemiacetal. Again, you can tell that's true because the carbon that has the two oxygens, one of them is an OR and the other is an OH. So that's hemiacetal. And this is we would call this a disaccharide. That's a way of saying two sugars linked together. You could also call this a glucosyl glucoside because you form an acetal between glucose and the other glucose. A couple of things about disaccharides. They have directionality. One side is different from the other side. Do you see that we sort of arrange the molecule sort of oriented this way with OHs on this side and hemiacetal or acetal carbons on the right? So there's an acetal carbon there and then another acetal carbon there. The other thing that you might notice is that the hemiacetal carbon all the way over on the right side is in equilibrium with an open chain form. You learned that last time, which in this case would be an aldehyde. So we call this the reducing end of the sugar. Okay, sorry. We got to figure that out. Sorry, let me just take a moment and tell it to use EduRoam. Or we can just turn Wi-Fi off. But what if I get an email? It'll be fine. Okay. So on the right-hand side, the hemiacetal end, we call this the reducing end of the sugar. And it's not such a big thing now. You'll get this terminology a little bit here and there. It comes from olden days where if you wanted to characterize a molecule, NMR wasn't available. but there were some simple experiments you could do to demonstrate whether a sugar had a free hemiacetal end. And one was a reduction reaction called the Tollens test. I think this is listed in your text, and I should have ordered the demo today. Maybe we'll do it next time. But basically, a sugar that has an aldehyde on it can be oxidized by silver, by a silver 1 salt to form metallic silver. And you can actually detect if your sugar has a free hemiacetal end, it will actually reduce the silver and sometimes that'll plate out on the inside of glass and make an interesting looking mirror. But anyway, it's an interesting qualitative test for what kinds of carbohydrates you have in your sugar. We would call this end, the end that has just the acetal, the non-reducing end, because the acetal is not in equilibrium with an open chain form. Some of these disaccharides have non-systematic names. This is called cellobiose. It's a component, it's a subunit of cellulose, which is a component of plant cell walls, or in other words, dietary fiber. The other thing we want to talk about here is the nature of the acetal linkage between carbohydrates A and B. We're going to call this linkage a glycosidic linkage because we're using the term glycoside to mean acetal involving sugars. And there's a way biochemists talk about glycosidic linkages that you need to be aware of and you need to be able to recognize and be able to use. So the first part of the glycosidic linkage, the first portion of the name of the glycosidic linkage describes whether we're dealing with the alpha or the beta anomer at the hemiacetal carbon. In this case, it's beta, so we'll call this a beta glycosidic linkage because that's the beta anomer, right? You see how the OR group on carbon 1 is up, equatorial, and it's on the same side as the up equatorial group at C5. That's why we're calling it beta. The next thing you do is describe the two atoms of the carbohydrates that are involved in the glycosidic linkage, starting with the acetal carbon. So that would be 1, and then you draw an arrow, and then you write down the number of the atom that is involved in that glycosidic linkage. So this is a beta 1,4 linkage. Okay? So you'll need to be good at recognizing that, for example, in cellobiose, A is beta D-glucopyranose and B is beta D-glucopyranose, and the linkage between these two carbohydrates is a beta 1,4 glycosidic linkage. Questions about that? Yeah. Would beta 1 always be the first part of that? So would the, not necessarily beta will not always be the first part. If the OR group was down, that would be alpha. For most carbohydrates, where the C1 is the hemiacetal carbon, yeah, it's going to be 1. Now there is a carbohydrate, fructose, which has the acetal carbon on C2. So in that case, it would be a 2 linkage. Okay, others? Okay, one question you might be asking is glucose has a lot of OH groups, like a ton of OH groups. And here, when we were making the methyl glycoside, all we had was methanol as our nucleophile. There was only one OH group to choose to make the hemiacetal, to make the acetal, the methyl glycoside. But with this cellobiose molecule that I've shown you, the precursors to this would have been we would have gotten this from 2 independent glucose molecules. So let's make them both beta. And the question you could ask is, how do you control which OH group on the carbohydrate acts as a nucleophile to attack the oxocarbenium ion as we showed in this step? And how do you control only getting the beta anomer versus the alpha anomer? So this is a question of two things. Number one, regioselectivity. If this one's going to be our electrophile and make the oxocarbenium ion, maybe I'll just draw that oxocarbenium ion directly like this. And this is going to be our nucleophile. And we want to make exclusively the beta 1,4 linkage. We need to deal with control of, first, regioselectivity, that is getting the right OH group to act as the nucleophile. In this case, we'd want this one. And then we have to deal with stereoselectivity, which is how do we get the OH group to attack from above so we can get the beta linkage instead of attacking from below so that we can get the alpha linkage. Those two problems are a major problem in carbohydrate chemistry, and people have worked long and hard to figure it out, and guess what? It involves a lot of protecting groups, and some that we actually are not going to talk about. But there are people who know how to do this and can do it pretty well. We got one of the world experts in our department, Professor Paul Savage, whose group can basically make any carbohydrate that you want. And it's tough, really tough, and it involves a lot of careful protecting group manipulation and a lot of chromatography to purify desired products from undesired products. But a question you could ask is, nature does this all the time, so how does nature control which nucleophile acts, which molecule acts as a nucleophile and which molecule acts as an electrophile, and how does it control regioselectivity and stereoselectivity? So what I'm going to show you now is not in your text, and you'll get to it in biochemistry, but I just want to give you a short preview of how nature does things. There are a lot of enzymes that do this, and they are called glycosyl transferases. And there are different enzymes that do this, but I'll give you an idea of one. Supposing you wanted to make, and again, I'm not referring to any specific carbohydrate or any specific enzyme, I don't have those details, but I'll give you an idea of what can happen. When nature wants to make a glycosidic linkage, nature doesn't need to use protecting groups because enzyme active sites position the electrophile and the nucleophile very close to each other and in an orientation such that the right group on the nucleophile attacks the right atom on the electrophile. The enzyme itself then becomes the great big protecting group that prevents undesired side reactions. The other thing the enzyme will do is it will convert the hemiacetal carbon into a good leaving group. So that leaving group is called UDP, which stands for uridine diphosphate. We'll learn about it later in our chapter on nucleoside chemistry. If you want a quick view of what this would look like, this is the bond that's attached to that oxygen, and then there's another phosphate. Oops. The D stands for diphosphate. Then there's a ribose ring with down OH groups, and then here is the base uridine. And there's usually a magnesium dication that is coordinated there. Basically, all of this is an excellent leaving group. Okay? So imagine that the enzyme is holding on to the carbohydrate. There's an enzyme active site that sort of holds on to the carbohydrate, positions it correctly. And then you have your second molecule of glucose that also binds in the enzyme active site. And close to the C4 hydroxyl, you have a group that can act as a base to remove that proton. And this is a group attached to the enzyme, likely some amino acid. It will deprotonate that alcohol and the C4 hydroxyl. Again, how does it deprotonate only the C4 hydroxyl and none of the other hydroxyls? Well, it binds the molecule in such an orientation that it's only the C4 hydroxyl that's close to the base. As that proton is being removed, the oxygen is about to become more negatively charged. As that happens, it attacks the C1 at the same time as the leaving group is leaving. So one of the ways the enzyme controls stereochemistry is, instead of letting the leaving group leave to get a planar carbocation intermediate as we do under acid-catalyzed acetal hydration conditions, the enzyme uses an SN2 reaction to control stereochemistry such that you can only get one stereoisomer. Okay? How does it do that? Well, enzymes are all about altering reaction mechanism to favor a particular pathway. So presumably, and I don't know this, but there are presumably features that prevent the UDP group from leaving until the nucleophile comes in and attacks. So when you see carbohydrates that are complicated and nature makes them, you're like, how did that happen? Why did we not get uncontrolled acetal formation on every OH group? The answer is because the enzyme basically acted as a protecting group. Now, if you were to take some glucose and mix it together with a small amount of acid and then just start boiling it, you'd be making rock candy, and that does involve uncontrolled acetal formation on most of the hydroxyls. And that's why rock candy gets so thick and eventually becomes a solid, because you've made so many cross-links. Okay? All right. So we talked about glycosidic linkages. We talked a little bit about glycosyl transferases. Questions so far? Yeah?
You said enzyme B, so that's an entirely separate enzyme?
No, enzyme B stands for base.
Oh, enzyme.
So what this means is a basic side chain in the enzyme active site. Good. Others? You're going to see a lot of what happens in enzyme active sites is catalysis of proton transfers. You have groups that are acidic, you have groups that are basic that can help turn things into good nucleophiles, help leaving groups leave, and so on. Okay. All right, let's just deal with some other carbohydrates. Incidentally, we haven't talked about how nature hydrolyzes carbohydrates. We'll maybe do that on our chapter on metabolism. But I'll say we don't have enzymes in our GI tract to digest this beta-1,4 linkage between glucoses. And this is why you don't get particular nutrition or calories from dietary fiber, because you can't hydrolyze that linkage. You can hydrolyze the alpha-1,4 linkage. So what I'll show you now is a disaccharide called maltose, and this is a disaccharide subunit of starch. All right, so here is, and it involves, again, just glucoses. So we're going to draw the other, it's going to involve the, we'll just draw glucose here with its C2, 3, 4, and 5 groups on it. Then C1 is going to be the alpha anomer. And then the oxygen involved in this disaccharide is going to come from C4 of the next glucose subunit. And then all the other groups are in the same orientation. Let's continue to make this C1 the alpha anomer. So we would call this glycosidic linkage, which I will highlight in pink, an alpha 1,4 linkage. That's the alpha 1,4 linkage between 2 glucose molecules. So you don't need to memorize that this is called maltose, but given its structure, you would need to be able to say that that's an alpha 1,4 linkage, and you'd need to be able to say that these are individual glucoses. Yeah?
Would there be a situation where like the first glucose is alpha and the second one's beta?
Would there be a situation where the first one is alpha and the second one is beta? Yeah, that seems reasonable. In fact, probably if it's immediately hydrolyzed from starch, it probably is like this, but you might expect a squiggly line, a mixture of alpha and beta anomers at that first carbon.
Do you have to name the second one? Like say
No, you don't. The glycosidic linkage is the part that the alpha refers to the configuration at the anomeric carbon that's involved in the acetal. Yeah. So we can be general and just put a squiggly line on the reducing end of the sugar because we don't know what the configuration of that one will be. And that is an alpha 1,4 linkage. Now your body does have enzymes that hydrolyze that linkage. And if you want to see well, perhaps not quickly, if you want to see the structure of starch, I can show you a couple of different forms of starch that you may have heard about. So if you link a ton of maltose subunits together, all with alpha 1,4 linkages, you have something that's called amylose. You ever heard of that before? Maybe. Food scientists out there, maybe. So let's do something you will hate, but it's going to save my hands. You don't need to actually copy. This will be available in the notes. You don't need to panic to scribble it all down. Let's see. So we'll copy that. Paste. Erase. Put there. Oops. Copy, paste, erase, and re-put there. And so it could continue on sort of indefinitely with lots of different, with squiggly lines indicating many more alpha 1,4 linkages. You can see that we have all the way through alpha 1,4 linkages, and that's amylose. And your body's pretty fast at digesting that linkage. If you don't believe me, you can do a really gross experiment. It's not that gross experiment at home. You could go buy some saltine crackers and take a swig of water, get your mouth moist, then put the saltine cracker in there and just sort of suck on it for a while. And it will gradually start to taste a little bit sweeter. It's never going to taste really sweet because actually glucose doesn't taste super sweet to your tongue. Sucrose does, but glucose is a little bit less sweet. But you're going to start to pick up a little bit of sweetness. And what's happening is enzymes in your saliva are breaking down those alpha 1,4 linkages and liberating glucose molecules. And that starts to happen in your mouth as you're eating. This week, it was a couple weeks ago, my dad turned 70 a couple days ago, and we were talking to my mom, what should we get Dad? Because when your dad's 70, he sort of just buys himself what he wants, and he doesn't really have that many needs, and so we're like, what should we get him? And my mom is like, well, he could use a little trash can for his office. Woo, that's super fun. Hey, when I'm 70, I'm going to tell my son to buy me Legos is what I'm going to say. But And then she said, well, he likes to, after dinner, he likes to eat crackers and he spreads butter on them. I'm like, and then suddenly I had this flashback to my childhood, and I can remember spreading butter on saltines, which I now think is weird, but as a child I remember doing it, and it must have been because my dad had done it and I had seen him doing it. Anyway, we'll talk about hydrolysis of fats and oils a little bit later, but that had nothing to do with the lesson other than we were talking about crackers, so go figure. All right. Oh, and then there are starches that are a little bit more complicated. So what I'll do is I'll draw for you amylopectin, which has not only alpha 1,4 linkages, but also has alpha 1,6 branch points. So you're really going to like this. Here's amylose. I'm going to need more space, so we're just going to scroll down. Here's amylose, and we're going to take the C6 hydroxyl of one of them, and we're going to make an alpha 1,6 glycosidic linkage with that C6 hydroxyl. So we'll take another chain. I told you you were going to love it. We'll take another chain of amylose, and we'll put it there, except I don't like the fact that that is small, whereas the other one's large. So that seems better to me. And then this one in blue is an alpha 1,6 linkage, and it's a branch point. So there are some starches that are more complicated, and amylopectin has that sort of branch point, Y-shaped kind of structure. And you do have enzymes that can hydrolyze that. It's called alpha glucosidase, and you can tell that it hydrolyzes alpha linkages because alpha's in the title. Okay, questions about that? The natural question asked at this point by nearly all students is, do I need to know that for the test? And my answer is, of course. Everything I say is vitally important. Don't you know this by now? But seriously, you don't find that funny. I find it hilarious, but you don't find it funny. The thing you need to know is, could you recognize each of those subunits as glucose? Could you identify the glycosidic linkages and name them? Okay, questions? All right, let's do a few more. Couple that you may be aware of. This is galactose because the C4 hydroxyl is up. And then this is glucose. We'll put a squiggly line on the C1 of the reducing end of the molecule. This is called lactose. Tell me, what is the nature of this glycosidic linkage? How would you describe it? It's 1,4 for sure. Is it alpha or is it beta? Beta. So lactose has galactose, and then a beta 1,4 linkage, and then glucose. This is sometimes how people abbreviate carbohydrates. They'll use a 3-letter abbreviation for galactose versus glucose, and then they'll put the beta 1,4 linkage there. This is the sugar lactose, and it's, of course, present in dairy, and then it's actually present in human milk as well, only in human milk there's an additional carbohydrate that's sort of present. So I'm going to draw the human milk oligosaccharide, and then we're going to talk about lactose intolerance. You can see that the human milk oligosaccharide shares the same basic structure. You've got the glucose and the galactose with the beta-1,4 linkage. But there's an additional carbohydrate that we won't talk about or name. And it comes branching off of the C2 group of galactose. We won't draw it in its chair form. We'll just draw it like this. So this is human milk oligosaccharide, and I just don't know off the top of my head, I'm embarrassed to admit, I don't totally know off the top of my head the identity of this sugar. It's either fucose or xylose, but I'm not sure. In any case, you can see the beta-1,4 linkage in both places, all right? Now, infants rely on milk. And so to get nutrition from milk, they need to be able to hydrolyze this beta-1,4 linkage. And so they make, in their intestines, they make an enzyme that probably has different names, but we could call it beta-galactosidase. Remember, the acetal is called a glycoside. It's a galactose on this side, so that's why it's called galactoside. The ase refers to hydrolyzing it, so a beta-galactosidase is an enzyme that hydrolyzes a beta linkage involving galactose as the sugar that has the acetal in it. Beta-galactosidase hydrolyzes the beta-1,4 linkage. Now, over time, before humans had domesticated animals, you stopped needing to get nutrition from milk, and so the expression of that enzyme would drop off in the intestines of human adults. And it wasn't a big deal because you weren't drinking a lot of milk because you hadn't domesticated animals, and so you were drinking water and eating roots and fruits and meat. You didn't need a lot of beta-galactosidase. So most humans were what we would call lactose intolerant simply because they didn't need to get nutrition from lactose. It's an interesting story in human history. I read it in a book I think called A Brief History of Everyone Who's Ever Lived, but it talked about how eventually as humans migrated out of Africa into other parts of the world, including Europe, animals were domesticated, and then in Europe there started to be an advantage, especially in cold times, to be able to get nutrition from dairy because you could make butter and cheese and store it and then eat it when things were cold. Challenge is, if you don't have beta-galactosidase, butter, milk, and cheese are going to make you feel sick. So people that had migrated into Europe over time, a mutation developed that allowed expression of beta-galactosidase in adults. So if your ancestry is predominantly European, you likely can eat milk and ice cream without a lot of trouble. If it's not, you might be lactose intolerant. It just sort of varies from person to person. My son Jack, the missionary, feels like he's lactose intolerant, but that ice cream is worth it, so he just powers through. But there are products that you can take that help you with that. Lactate is one of them, and it basically is preloaded with the enzyme that hydrolyzes the lactose to help you out a little bit. Okay, so that's lactose. I guess the last one we should draw is table sugar, which is sucrose. Sucrose is kind of weird because unlike the other carbohydrates we've learned today, in which there is always a reducing end, a hemiacetal end. There's one in maltose, there's one in cellobiose, oh, shoot, there's two things I wanted to do yet, so we'll just proceed. In sucrose, there isn't a reducing end because it turns out in sucrose, the two hemiacetal carbons are actually linked to each other. So sucrose involves one molecule of glucose, like this. Here's the C1OH, the C1 carbon, and then here's the oxygen. But that oxygen is attached to to the acetal carbon of another carbohydrate. So I'll draw that carbohydrate for you here. It's a 5-membered ring sugar called fructose. Dun, dun, dun. This is C1 of fructose, C2, C3. The OH on C4 is down and back. And then here is C5 and then 6. So this portion is called fructose. This portion is called glucose. Put together, that's sucrose or table sugar. It's kind of difficult to tell what you should call this linkage. It's definitely a 1-2 linkage, but there's anomeric carbons on either side. Do you see how this C1 is a acetal carbon? But do you see how this one is too? That C1 is attached to 2 OR groups. So this is why they call sucrose a non-reducing sugar, because there is no free hemiacetal. There's no hemiacetal, it's an acetal on both sides. You could say that the configuration of this carbon is alpha because this oxygen is on the opposite side of the ring as the C5 hydroxymethyl group. However, over here, you would say that the configuration of this carbon is beta because it's on the same side of the ring as the C5 hydroxymethyl group. I'm not sure how they name the glycosidic linkage in sucrose. Is it alpha 1,2 beta or something? I'm not sure. We could look it up. It doesn't matter. I won't ask you to name it. But sucrose is unique in the sense that it's a non-reducing sugar. And of course, your body can hydrolyze that linkage to liberate both glucose and fructose. And we'll learn in our chapter on metabolism what your body does with glucose and fructose. Okay, one more thing. There are carbohydrates in which C2 is an amine instead of an OH group. And so you will have heard of some of these. Here is a molecule called glucosamine, in which the C2 group is an amino group. And then often in nature, that C2 amino group has been modified with an acetyl group. So this is called N-acetyl glucosamine. And these are found all over the place. In particular, though, N-acetylglucosamine is a component of chitin. Chitin is bug shells, insect shells, right? The strong, rigid casing of insects. Chitin is the polymer. The disaccharide is called chitobiose. And this is just two N-acetylglucosamines linked together through a beta 1,4 linkage. Glucosamine is also found in components of the extracellular matrix. You should be able to recognize glucosamine and N-acetylglucosamine. And there are also galactose and mannose versions of glucosamine, where the way you know to put the amine there in the name is just you look for the amino group on C2. And it's only ever on C2. It's never on the others in most common carbohydrates. Okay, so that concludes carbohydrates. Next time we are moving on to lipids, chapter 25. So see you Wednesday.